In all of human history, our skies have been ruled by a single sun, the singular source of light, warmth, and gravity that defines every rhythm of life on Earth. It is constant, solitary, and stable. Yet when studied from the perspective of our galaxy, that very loneliness is the exception, not the rule. Most stars are not alone. They circle one another in pairs, trios, or even knots of light bound by complex gravitational choreography. Where such clusters exist, so too may planets, worlds that rise beneath two suns, or three, or even seven. And their skies, unlike ours, flicker with endless dawn. The simplest of these complicated systems is the binary star. Two stars orbiting a common center of mass called the barycenter. If the stars are roughly equal in mass, their dance is beautifully symmetrical, twin orbs tracing perfect ellipses around an invisible midpoint. When their masses differ, the heavier partner moves little, dragging the lighter companion in a wide, looping arc. For centuries, astronomers wondered whether planets could exist in such celestial marriages. Early thinkers dismissed the idea. The tug-of-war between two centers of gravity, they reasoned, would tear any potential world apart. But the universe, with its talent for subtlety, proved them wrong. It turns out there are two stable ways for a planet to survive in a binary system. The first, called an S-type orbit, allows the planet to circle just one of the two stars directly, much as Earth circles our Sun. The second star, far away, becomes a brilliant companion in the sky, sometimes bright enough to cast a second shadow. The second, a P-type orbit, places the planet on a much wider path around both stars simultaneously. In this case, the twin suns are locked together in the heart of the system, appearing side by side in the sky as they rise and set together. Under the right conditions, both configurations can be stable for billions of years. Gravity, it seems, doesn't mind sharing. In 2011, NASA's Kepler Space Telescope discovered a world that turned theory into reality. Kepler 16b, affectionately nicknamed the Tatooine planet, after the fictional desert world with two suns. Kepler 16b is a gas giant roughly one-third the mass of Jupiter. It circles a pair of stars about 200 light-years away in the constellation Cygnus. To an observer on its cloud tops, the larger orange-hued primary star would blaze about twice as large as the sun in our sky, while the smaller, dimmer companion would appear like a brilliant ember orbiting near it. Every 23 days, one would eclipse the other, producing an unending ballet of shifting light. During Kepler's years of operation, the telescope detected several more such worlds, planets circling twin stars as serenely as ours orbits one. Each discovery added weight to a growing realization. Multiple suns and stable planets are not mutually exclusive but surprisingly common. If two stars can host a planet, what about three or more? Nature, as it turns out, has experimented there as well. In triple star systems, two of the stars typically form a tight binary pair, with a third companion orbiting farther out. The geometry preserves stability. The inner pair acts as a single massive entity, while the outer star circles at a safe distance. A planet might orbit only one star, both inner stars together, or, rarely, all three at once if it lies far enough away. Each configuration generates its own rhythm of eclipses, tides, and seasons, crafting skies of almost science-fictional splendor. Theoretically, these hierarchical arrangements can scale upward. Astronomers have identified systems with 5, 6, even 7 stars gravitationally associated. Though such higher orders are exceedingly fragile, for a planet orbiting within them, the heavens would never be still. Constellations would shift not across centuries but across a single day. Simulations show that a 7-star world, orbiting far from the chaos of its core suns, would see its skies painted with faint shifting orbs, each star waxing and waning as their orbits carried them behind one another. From the planet's surface, daylight might resemble the glow of multiple moons rather than blinding sunlight. Dusk would never truly fall. Shadows would mingle and multiply, tangled beneath a sky in perpetual glow. What would life be like on such a world? Imagine standing on soil beneath two dawns. The first sun climbs the horizon, casting long amber beams. Minutes later, the second rises, washing the land in a second flush of gold. Two overlapping day-night cycles merge and diverge through the year, reshaping every rhythm of life. For a planet like Kepler-16b, each star's warmth contributes a small portion of the total energy its atmosphere receives. If such a world were rocky and Earth-sized instead of gaseous, its seasons would not follow simple monthly or yearly patterns, but the complex beat of its suns. When both stars aligned on one side of the planet's orbit, their combined heat could trigger scalding summers. When one retreated to the far side, deep winters would settle in. Civilizations, were they to arise there, might mark time by the harmonies of their twin shadows. Closer pairings bring greater challenges. If two stars orbit one another tightly and a planet circles them at just the right distance, temperature extremes could remain bearable. But most binary systems alternate between relentless exposure and long darkness. Habitability there would be a fragile balancing act, possible only if atmospheric and oceanic currents spread energy efficiently across the globe. Nature's variety extends further still. Not all stars are sun-like. Many are red dwarfs, cool, small, and temperamental. Despite their mellow glow, red dwarfs unleash violent flares capable of bathing nearby planets in lethal radiation. If Earth orbited a red dwarf beside our Sun, the sky would pulse unpredictably. Massive solar storms could tear at our satellites and streak auroras to the equator. A planet trapped between a yellow sun and a red dwarf might endure alternating seasons of brilliance and cosmic lightning. Pair that with a massive blue or white star, and another scenario emerges. Blue giants are titanic furnaces, millions of times more luminous than the sun, but short-lived. If such a colossus were part of a binary with a smaller star, any planet caught nearby would face catastrophic winds and radiation. Its atmosphere could be stripped in centuries. And when the giant eventually died, exploding into a supernova, the blast could sterilize entire systems for light years around. Distance offers respite. Some binaries are separated by thousands of astronomical units, so far that their mutual orbit takes millennia. In such systems, a planet could circle one star in relative peace, while still calling another sun its distant neighbor. To its inhabitants, that second star might appear as a brilliant, unmoving beacon in the night sky, a cosmic lantern that never sets. Astronomers long assumed that binaries outnumbered single stars. The brightest stars we see, Sirius, Polaris, Alpha Centauri, are all multiples. But advances in detection have refined that picture. Today we know that about half of all stars belong to multi-star systems. For sun-like stars, singletons are actually the majority. Still, in a galaxy of 400 billion stars, half leaves billions of potential multi-sun systems. Each one could host planets unlike any in our experience. Mass plays a role. The mightier a star, the more likely it is to form with companions. The greatest blue giants emerge from dense stellar nurseries where material collapses in clusters. Red dwarfs, on the other hand, the most common stars in the galaxy, are often solitary. Our Sun, a middleweight yellow star with no twin, sits intriguingly between categories. It may be neither rare nor typical, just another expression of cosmic variance. Could any of these complex systems nurture life? Computer simulations suggest yes, but only in narrow zones where gravitational stability and moderate temperatures coexist. In binary systems where the stars orbit close together, the habitable band lies farther out, a ring encircling both stars like a wide racetrack. In wider binaries, each star maintains its own smaller zone, and planets must cling closely to one star or risk being flung away. Atmospheric dynamics would make these worlds spectacularly unpredictable. Clouds might form along meridians aligning with dual sources of heat. Winds could reverse direction as the secondary sun set in one hemisphere while the primary rose in another. Even biological rhythms, if life evolved, would synchronize not to daily cycles but to the ever-changing patterns of dual sunlight. In stories of old, two suns symbolized eternity and duality. In astrophysics, they represent resilience, a planet's tenacity to find balance between chaos and gravity. If humanity could stand on a beach beneath twin suns, we would see more than a spectacle of light. The overlapping shadows on the sand would tell of invisible forces in perfect tension, equations held in grace. Each reflection glimmering on the waves would carry photons that began their journeys from two separate hearts of fire, meeting only in that moment across light years of distance. And there, beneath the twin suns, one might realize that our single daylight is just a quiet variation of a grander theme. The universe experiments endlessly, with solitary stars, with pairs, with trios, and tangled families of light. In every case, planets find a way to exist. Gravity, after all, writes symphonies as easily as it writes orbits. 2 stars, 7 stars, or 1. The outcome is the same. Worlds emerge, night follows day, and somewhere, perhaps, eyes look up at skies unlike ours and count not one rising sun, but many,